Okay, so lesson 49, concavity and inflection points, what have you already read for us, right? Geometric meaning of second derivative, first and second derivative test. So we've learned a lot about first derivative already, yes? And first derivative helps us know if a graph is increasing or decreasing. Okay, so second derivative is going to talk about concavity. And I don't know, you guys didn't seem very familiar with the word concavity.
Concave is like on a wheel.
Well, I was going to say, kind of relates to the whole concave convex thing. Although at this point in my brain, I don't even remember convex, but because I have calculus on the brain.
I think convex is like
I don't know.
Yeah.
So, okay, so we talk in calculus about something being concave up and concave down. So when we talk about concavity, notice it says the concavity is the bowling of the graph. So when we talk about something being concave up, the graph will be bowled up. So kind of like there's a minimum, or there is. So if a graph is concave up in a certain section, there's a minimum in that. So kind of like right here, you see like a right side up parabola. That graph is concave up because the graph is curved up. So it's not, there's increasing and decreasing involved, but it's curved up. Whereas concave down, if the graph is concave down, it's bowled downward. And basically if a graph is concave down, that means that there is a maximum in the graph because that graph is curved and facing downward. Where the concavity changes. So I've mentioned this, for instance, on y equals x cubed. If you think about the cubic graph, there is what we have called an inflection point. And so like right here, this is just a mini sketch of y equals x cubed. And if you think about y equals x cubed, it looks like this, right? There's your bigger version of it. And at 0, 0 is an inflection point. Because what's happening is up to 0, 0, your graph is bowled down officially. Even though it doesn't continue going down over here, this section to the left of 0, 0 is concave down because it kind of is curved downward. Is that what I want to say? I don't know. You guys know what I mean, right? Okay. Whereas to the right of 0, 0, after you pass through it, it's more curved up. Okay. It's bowled upwards. And so that's an inflection point. An inflection point is where your concavity changes, whether it be from concave up to concave down or vice versa. And so Ross was laughing at Pip. In all honesty, I thought you said pimp at first when you said that. I was like, we don't have pimp in the notes, do we?
Oh, no, but I can put pimp in my notes.
I knew you were going to do that as soon as I said that. So Pip, P-I-P, possible inflection points. Okay, and notice, what does it say about inflection point? I don't know if you guys can read that or not. That's where the second derivative equals 0. Okay, so first derivative equaling 0 is mins and maxes. Second derivative equaling 0 are possible inflection points. This will forever go down as a day in Ross's calculus notes that Mrs. Sargent talked about pimps. Right? Since he puts all these notes in his notes.
Well, so yeah, I put pimp and I made a little acronym, it's a possible inflection mathematical point.
There we go. Okay, you made it mathematical. Okay, so let's look at example 1 here and just make sure we kind of have an understanding of what concave up versus concave down appears to be. So shown below is this graph of f. Indicate if the graph appears to be concave upward, concave downward, or to have an inflection point at the points labeled. So concave up, I'm going to use CU. Concave down, I'm going to use CD. And inflection point is IP. So we have to do what? A through F? A, B, C, D, E, and F. And we're going to talk about each of these points. So, when you're ready, thoughts on A. What is my graph doing there in terms of concavity?
Concave down.
Concave down. It's part of something that is bold downward, right? So A is concave down. What about B?
That also be concave down.
And B is a maximum. Well, I think that's supposed to be the maximum there. Isn't that what that looks like? And so when you have a maximum, that is going to look like that is going to be part of concave down. Okay. C. Yeah. C right there is where my graph is changing. It was bold downward, it was concave down, and now it's changing and going to be bold upward. So C is an IP, an inflection point. What about D? Okay, it's a minimum, so it's definitely bold upward at that point and concave up. E? Notice kind of those big long straightaways between a min and a max. There's an inflection point somewhere on that big long straightaway. And so that's what E is supposed to be, is your inflection point. F. Yeah. Concave down there. Okay. Is there a little bit of understanding there? Questions? This is the easy part, right? Well, yeah, that's the easy part. Are we dangling because that's the easy part?
Yeah, I got excited.
Okay. So, geometric meaning of the second derivative. So, what you need to, so calculus. Basic calculus, the first derivative and increasing, decreasing goes together. The second derivative and concavity goes together. Okay? So, determining concavity inflection points is similar to what we did to find max min values. We simply use second derivative instead of the first derivative. So if you recall, we would take the first derivative, set it equal to 0, and that would help us find, we call them critical points, right? And those critical points are usually mins or maxes. Okay? So now, it's going to be the second derivative. And the second derivative is going to, and I guess let me back up. So first derivative, you had the mins and maxes, right? And then in between the mins and maxes, depending on whether the derivative was positive or negative, told us if it was increasing or decreasing. So now with second derivative, the idea is if we set it equal to 0, that finds our inflection points. And then between the inflection points, your graph is either positive or negative. A positive second derivative is going to be concave up. A negative second derivative is going to be concave down. And that's what a lot of the rest of this page says right here in the next two sections. And so let's see. If the second derivative is positive, okay, so when if the second derivative is positive when x equals a certain point, then the slope of the graph of the function is increasing as the x-coordinate increases. Thus, the graph is concave upward. Okay. And so, reread that, catch what that says, because this is the difficult part to understand in kind of my view. The slope of the graph is increasing. So when we do the first derivative and we talk about whether a graph is increasing or decreasing, we're just looking at the graph, is the slope positive or negative. Now we're looking at, is the slope increasing or decreasing? Okay, so the slope of the function is increasing as the x-coordinates increase. And so So if you have your inflection point here as your critical point, so to speak, if to one side it is a positive second derivative, that's going to indicate concave up. Okay? Then the other part of this says if the second derivative is negative, when x equals that critical point, then the slope of the graph of the function is decreasing as the x-coordinate increases, and the graph is concave down. Okay, and again, we're going to practice this. I think it's more on the next page. So when you have your inflection point and you have negative to one side or the other, then that says it is concave down in that area. Note what it says. Excuse me. The first derivative, remember, actually told us the value of the slope at a certain point. Because a slope, if it's a positive slope, it's increasing graph. If it's a negative slope, it's decreasing graph. So first derivative told us the value of the slope at a certain point. Now, look at example 2. At which of the points labeled on the graph shown is the second derivative positive? Think about that for a moment while I take a drink. What does it ask us? I mean, other than at which of the points is the second derivative positive?
It's asking where is it concave?
Okay. Can you guys see this color okay for the moment? As long as I don't write anything too important with it. I like this color, but I know it's not as visible as some of my others, so at least not on a white screen. Okay, so we want to know where is this graph concave up? And so and I will say, by the way, second derivative positive, we're looking for when the second derivative is greater than 0 is another way to think about that. So any thoughts? C is a definite, yes. C is a minimum. So if C is a minimum, it's definitely concave up. Minimums and concave up go together.
I was going to say D could also be, because it says the arrow is pointing up instead of like going back down, which means it's not an inflection point, which means it has to be the same as the one before.
Okay, so at this point, once that graph gets past D, do we have any indication that it ever turns and goes back down? No. If we had indication that it turns and goes back down, D could possibly be an inflection point. But based on the fact that my graph is continuing to go up, that leads me to believe my graph goes up infinitely. And so my graph is going to, the entire rest of the graph is going to be concave up. So I would agree with C and D. A would be concave down. B is probably an inflection point because it's between the two. Okay, so that means at A, my second derivative would be negative. At B, my second derivative would be 0 because the inflection point, the second, it's like a critical point. Okay, and this I just realized this wasn't labeled. I try and make sure my graphs are labeled. That was just the graph of F. As opposed to, they sometimes like to give you the graph of F prime or F double prime. Okay.
Words.
A lot of words, huh? Okay, so next page, we've got to talk about first derivative and second derivative tests. I would kind of like to believe, if I'm thinking right here, you guys are already familiar with the first derivative test. We haven't called it that, but I think the concept is there for you. Okay, so suppose f prime of a value equals 0. So when that first derivative equals 0, that C is now a critical point, right? Min or max, I agree. Officially, I'm going to say critical point. Okay, min, max, or on occasion, it could be an inflection point. So we just call it a critical point, but yes. Okay, so C in this, as we talk about C in here, it represents a critical point. If the derivative of f, so the slope of the graph of f, is positive. So if the first derivative is positive for all values of x, just to the left of C, just to the left of the critical point, and negative for all values of x just to the right of C, then f of C is a local maximum. So if the derivative is positive to the left of C and negative to the right of C, then we have a maximum on our hands. So think about this. Okay? Here's C. Here's my visual for C. If to the left of C, the derivative is positive, what is the graph doing to the left of C if the first derivative is positive? It's going to be increasing to C, yes? And then it says all value, and then it's to the left of C, the derivative is negative. What's the first derivative doing when it's negative? It's telling me that my original graph is decreasing. So does it make sense that C is a maximum then? That's what that says in all those crazy words. I know you think kind of like, ugh, words. I agree. But we have to dissect it. That's what number one is saying right there. If your derivative is positive before the critical point and negative after the critical point, then that's a maximum in question. So can you guess what 2 is going to do? If the derivative of f, so first derivative, is negative for all values to the x left of C, and positive for all values of x to the right of C, then f of C is a minimum. You want my visual again? Okay, so my first derivative to the left of C is positive. So what's that indicating if it's positive? Wait, no, I just totally read that wrong. Okay, negative to the left of C. So if my first derivative is negative, that means the graph of f is decreasing. And then if the first derivative is positive to the right of C, then that means my original graph is increasing. So there's the visual. Does it make sense that C is a minimum then? Okay? Okay, part 3. If the derivative of f has the same sign for all values of x to the left and right of C, then the point, which would be C, comma f of C, is an inflection point on the graph of f. Okay, so same sign for values left and right of C, then we're talking inflection point. Honestly, we don't see the inflection points in the first derivative test a whole lot. Usually the first derivative test will give me mins or maxes. Okay, little friendly reminder right here. If the first derivative equals 0, we've already talked about this a couple of times today. If the first derivative equals 0, it's a critical point, critical number. If the first derivative is greater than 0, aka positive, my graph is increasing. If the first derivative is less than 0, aka negative, then my original graph is decreasing. And when we talk about a first derivative being positive or negative, that means if you look at the graph of the first derivative, negative means below the x-axis, positive means above the x-axis. Okay? Okay, that's our first derivative test. Now we're going to talk about the second derivative test. Second derivative test. Suppose f prime of C equals 0. wonder if that's supposed to say F double prime right there. I think it could be written either way, though. Okay. If the second derivative of F is negative at the critical point, then F of C is a local max. If the second derivative is positive, then F of C is a local min. Now, think about if this makes sense. First of all, we're talking second derivative. What does second derivative tell me? Concavity. What's a negative second derivative tell me? Concave down. A graph that is concave down has a max. Yes? Because concave down, think upside down parabola. So does it make this sense then that a second derivative, a negative second derivative, indicates a max? And I'll be honest, I don't remember the second derivative test very well. I think more, okay, second derivative, concave down, okay, max. I personally don't go negative second derivative means max. I kind of go the long way. Negative second derivative means concave down means a max. Okay? And then, so, if a second derivative is positive, a positive second derivative would be concave up. Concave up is going to be a regular parabola, as an example, and that would mean a local minimum. Can you follow my reasoning there? Okay? You connect in your brain however you want. You get it locked into your brain however you want. But that's the information. Really glad I didn't try and record this one. I would have been so frustrated trying to record this one. Okay, let's look at example 3. Suppose f is a polynomial function such that the first derivative at 3 is equal to 0, and the second derivative at 3 is equal to 3. Sketch the graph of f for inputs close to 3, and indicate the property of the function f at x equals 3. Got it?
A lot of F's and 3's.
There are. But it's good that it's all 3, that we're talking about 3's, because we want it all to be the same x value. Okay, so let's go with, okay, the first information they give me, f prime of 3 equals 0. Let's start with that information. What does that tell me about the graph of f?
So 3 is a critical number.
And why is 3 a critical number?
Because f prime of 3 is 0.
When the first derivative equals 0, that's a critical point, right? My first derivative equals 0, and so there is a critical point at x equals 3. And that means, what could possibly be happening at that critical point? Okay, yep. Min, max, or an inflection point. We don't know what right now. We don't know any other information, but that's what we have. Are we good with that information? Okay, so suppose f is a polynomial function, such that the first derivative equals 0, and then the second derivative at the same x value, right? It's important they gave us all the same x value. Of course, they had to happen to say it equals 3. Could have lived without that one, be a 3, but the second derivative of 3 equals 3. What does a second derivative equaling 3 tell me?
Positive, so it's increasing.
It doesn't tell me increasing. Okay, so it is important to notice that this 3 right here, I have to specifically point to which 3, right? That 3 is positive. It's a second derivative that's positive. And so when the second derivative is positive, that tells me, okay, my brain says concave up, but then concave up leads us to say minimum, right? So because this equals a positive value right here, my second derivative is equal to a positive. If my second derivative is equal to a positive, that's a concave up. So at that point, we would expect there to be a local min. And so for that reason, now we can go back and say, okay, yeah, it was a min, max, or inflection point. It is a minimum. It said to sketch the graph of f for inputs close to 3 and indicate the property of the function of f at x equals 3. What am I basically sketching? Some version of a curve, right? Where there is a minimum at 3. Okay, that's about what I know there. Whether you call it a parabola, whether you call it, you know, whatever. But some curve where you have a minimum at x equals 3. Indicate the property of the function means I took a moment and I wrote the word min and pointed at it.
So the property of the function is min, max, not whether it's concave up.
Right. Yeah. The property of the function is, I don't know how to explain. Yeah, it's the minimum or maximum that they're looking for.
Okay.
Did you guys figure out how we followed that? I guess the key is, can you follow my chain of logic? If you can follow my chain of logic, we're all good. And I do, as you get better at this, your chain of logic speeds up. Right now, take it slow. Okay, we ready for the next one? Suppose f is a polynomial function such that f prime of 3 equals 0, f double prime of 3 equals 0. In addition, f is positive for all values of x near x equals 3. Sketch the graph of f near x equals 3 and indicate the significance of the point on the graph of f at x equals 3. Just because you want some more 3's in your life and f's, right? Okay, so I'm going to dissect it bit by bit. Maybe you're already to the final answer. More power to you if so, but for the rest of us, I go slow on this stuff. First derivative at 3 equals 0. What does that tell me?
Min, max, or inflection.
Okay. There is a critical point, and that critical point could be a min, max, or inflection point. And I write this down so when you look out later, you can think about all the possibilities. So you're good with that. The second derivative also equals 0. So what do we know when the second derivative equals 0? Inflection point? It's either a min, max, or an inflection point. If it was a minimum, we'd have to be talking concave up, and we'd have to have the positive second derivative. If it was a maximum, we'd have to be talking concave down, and the second derivative would have to be negative. Since that second derivative equals 0, we are talking about an inflection point. Okay? And there was something else. In addition, f prime is positive. So I just wrote f prime is greater than 0. And I guess it did say near x equals 3, which is all that we're talking about right now is the graph near x equals 3. So f prime is positive near x equals 3. If the first derivative is positive, then that says my graph is increasing. Okay, well, you guys are going to have to tell me what to draw, because sketch the graph of f near x equals 3 and indicate the significance of the point on the graph of f at x equals 3.
So it would be looking like a cubic. Start from down, go up. There's an inflection point at 3, and then go up the other way.
Okay. If my entire graph, at least for what we're drawing, is increasing, it's got to be going up the whole time. But there's an inflection point. Okay? So there's an inflection point at 3, which means, yeah, you're going to have a cubic because there's that point when it changes concavity. In this case, because it's increasing, it changes from concave down to concave up. If it was decreasing, it'd be changing concavity the other way. And what's the significance of the point on the graph at f of x equals, or at x of f at x equals 3? That is an inflection point. Okay. Moving along. I've got to keep us moving if I'm going to get done on time here. So I have, 2 examples, but they're kind of bigger examples. So, given f of x equals x to the 4th, use f prime and f double prime to describe the graph of f near x equals 0. Now, good news is if you can visualize the graph of f of x equals x to the 4th, then you know what should happen, but it's understanding and making sure that it legitimately does happen. So, it told me to use f prime. So, what is f prime of x to the 4th? Okay, first derivative, move the 4 out front, subtract 1 from the power, so 4x to the 3rd. That's old hat by now, I hope. Now, it says near 0. So here's the deal. I need to go through and think about, like if you think about a number line, here's 0 in the middle, right? How do I decide what's going on to the left? Yeah. Well, and actually, I guess, did I do it? I don't know if I really showed it in my notes. Okay, so first of all, we need critical points. Well, I guess no, it said near x equals 0, didn't it? So realizing, I guess, you guys realize what's happening at x equals 0?
Well, for an x to the 4th graph, since x equals, or since we're going near x equals 0, wouldn't it have to be an inflection because the first derivative and second derivative would both equal 0? Or would it be the minimum of the whole thing?
Hold that thought. Okay. And here's, I guess it says, I'm trying to think about this a different way than what it should be. It tells us near x equals 0, right? So we need to see, okay, what's happening at x equals 0? We need to see what's happening to the left of x equals 0. What's a good value to the left of 0? And then we're also going to need to see what's happening to the right. Okay, because if we want to know what's happening near x equals 0, we got to know what's happening on the left, the right, or the left at that point, and the right. Okay, so when you put -1 into your derivative, what do you get? -4. When we put 0 into the derivative, what do you get? 0. When you put 1 into the derivative, what do we get? My brain had a moment. I forgot about the 4. Okay, so this derivative is what? It's -4, which means it is negative. What does a negative derivative tell me? Decreasing, yes? It's less than 0, it's negative. So my graph at this point is decreasing. What about over here?
It's increasing.
When I have at 1, I got a positive response with +4, which is greater than 0. When my first derivative is positive, we are increasing. And then when the derivative equals 0, what is that officially? That is officially a critical point of some sort. So, what does all that information tell me is happening at x equals 0 right now based on the first derivative? There's a minimum because we're going down, we're at a critical point, and then we go back up. So all of that information, I can decide or I can derive that there is a local min. And that's based on your first derivative information. Now, we were also asked to talk about the second derivative, yes? So what is our second derivative? Second derivative is what? 12x squared. Multiply by the 3 out front, subtract 1 from the power. And again, so we want to inspect the second derivative at 0. And we can use the same -1 and +1, yes? So what do you get when you plug -1 into the second derivative? 12. What do we get when we plug +1 in? What do you get when we plug 0 in? 0. So this second derivative is positive. Yes? This second derivative right here is positive 12, or it's greater than 0, so positive. Second derivative over here is greater than 0, or positive. What's that tell me? And?
That there's an inflection point.
Not necessarily, it's not an inflection point.
That there's a pip, which also could be a max or a min, too.
Okay. What about concavity?
Since it's 0.
Well, but right here, positive,
Okay, positive.
a positive second derivative and a positive second derivative indicates that this graph is concave up. Indicates that the graph is concave up. It confirms our local minimum, doesn't it? In that on both sides, we're talking concave up. And because we'd already looked at the first derivative and knew the local minimum, that's what helped us out there. Okay? Did I get everything? I think I got everything on that one. And what did it say? It said describe the graph of f near x equals 0. Well, there is a minimum and the graph is concave up around it. Okay? One more? Okay. Example 6. The graph below represents, note that, f double prime. Always, I keep saying this, right? Pay attention to what they tell you the graph is. They will always tell you what that graph is. You just have to watch for it, okay? The second derivative of f. Discuss the basic shape of the graph of f. So remember, this is the second derivative. So what we want to talk about here second derivative. When's my second derivative positive? When's it's negative? These are the type of things we want to talk about. So what do you notice over there?
It's positive above -2.
Or how about to the left of -2? My second derivative is positive. If my second derivative is positive, what's that going to mean about f? If the second derivative is positive, the original graph will be what at that point? Concave up. Because when your second derivative is positive, that will indicate concave up. And there's another spot that that same thing happens, yes? And that is when x is to the right of 2. Notice my second derivative is positive, which means my original graph will be concave up. What's happening between -2 and 2?
It's a negative.
My second derivative is negative. If the second derivative is negative, what is that saying about my original graph? Concave down. Okay. And what's happening at -2 and 2? Those points are equaling 0. And so when the second derivative equals 0, well, and we'll talk about, it's some type of critical point, right? But when the second derivative equals 0, we usually tend to think inflection point, okay? So here's what, I'm going to write this out. Do I have time? Oh, Lordy. Okay, so when x is less than -2, right? The very beginning of my graph. When x is less than -2, what did we decide about the second derivative? The second derivative of x was positive, or in other words, greater than 0. And what did we say that means about the graph then? The graph is concave up. What I'm trying to do is take what we already talked about on the graph and put it into appropriate mathematical language. Are we okay with what I wrote there? So when x is less than -2, so to the left of -2, the second derivative was positive, that's concave up. And then the next part we have, I'm going left to right, so then when x equals -2, our second derivative equals 0. And so when our second derivative equals 0, we're talking IP. Now in the next one, I'm looking at the section between -2 and 2, which means I'm going to write that as -2 less than x less than 2. So when x is between -2 and 2, my second derivative of x is less than 0. And when that's less than 0, when the second derivative is less than 0, it's concave down. When x equals +2, my second derivative equals 0. And there we're talking about an inflection point again. And again, it's an inflection point because my concavity is changing. Okay, that's what I forgot to mention earlier. Kind of poofed out of my brain. The concavity changed, so it's an inflection point. As opposed to if the concavity didn't change, my aha moment to myself. Up here, the concavity didn't change, so it was a min or a max. Here, my concavity changed, inflection point. Then the last part we have is for when x is greater than 2. Our second derivative was greater than 0 again. Positive second derivative indicates concave up. Now, can you visualize this graph? It's concave up, inflection point, concave down, inflection point, concave up.
So it is the absolute value of the parabola that starts below the x-axis.
Interesting. Not what I would have called it, but. And here's something else I look at. This second derivative basically looked like a parabola, right? So if the second derivative is x squared, the first derivative is x to the third, and that makes the original graph x to the fourth. But this is not just your basic wide parabola x to the fourth. This is more the W looking x to the fourth. So I'm going to say looks more like this because you have concave up, you have an inflection point right in there somewhere, concave down, an inflection point right in there somewhere, and then going back up. And so, bless you, that first inflection point would be at -2. That second inflection point would be at 2. I didn't dare try and, what? Okay, I didn't dare try and draw this on an actual grid. I still thought I had a couple minutes. Gosh. Okay. Busy week ahead of us, I guess. Problem set 49 tonight.
The test this week will be Friday.
Problem set 49 tonight. In problem set 50, if you haven't already looked at the 49 problems, go back and do that also. Sorry, a couple extra problems tonight. Okay? Go back and do that. So at some point, we're up to 2 homeworks to check, and you guys haven't gotten to see your test yet. And we are online for a test on Friday, is where we're at. Okay? Got everything?
You know that I get.